My name's Darryl. I'm from the Laser Center, and I'll be speaking about improving the brightness of a commercial laser system. Now, the brightness is defined as the power emitted per unit surface area per unit solid angle. So it describes the potential of a laser beam to achieve very high intensities while propagating over very long distances. Now, this is particularly useful in applications such as free space optical communication, target designation, as well as range finding. Now, the brightness is directly proportional to the output power of a laser. However, it's inversely proportional to the square of the beam quality. So ideally, you would want maximum power and a very, very low m squared. Now, the ideal beam for such a case would be the traditional Gaussian beam, much like the beam that you get from this laser pointer. And a very standard way in selecting this type of beam is by using a plano-concave laser configuration and by simply aperturing the cavity. In doing so, we are able to select this beautiful Gaussian beam, which theoretically has an m squared of 1. However, it has a very poor energy extraction, because the area where the Gaussian beam exists inside the laser crystal is quite small. So you would imagine that although we have this very nice beam coming out, the output power is quite low, and inherently the brightness would be quite low. So in order to get the power up, we can change the configuration by changing the curved mirror to a flat mirror, removing the aperture from the system, such that the modes that fit inside the actual laser can fit through the entire crystal. So here we're extracting a lot of energy out of the system, but we're also allowing a lot of other shapes of light to exist in the same process, thus leading to a very poor m squared. So again, our brightness is quite low. So we would want to actually try and marry those two concepts together, where we would like to get a Gaussian coming out of our cavity that has a very good m squared, and we'd like a very large beam going through our laser crystal, much like a top hat beam or a flat top beam. So our idea is to use two phase optical elements or phase transformation elements, where the idea is quite simple, is that if we start with a Gaussian beam that has a flat phase, we can then use the first element to transform this Gaussian into a flat top at some point. This flat top will then have a very complicated phase structure, but if we take the inverse of that structure and make the second element out of that inverse, then the output would be a flat top with a flat phase. So we start with a beam of a flat phase, we end with a beam of a flat phase, which means that this process is reversible. And if it's reversible, I can then add two mirrors on either side of my elements. I can pop in my laser crystal on this side, and in doing so, I should be able to have a very stable cavity. Now, we talk a lot about phase and phase transformation and a flat phase, but I'd like to try and visualize phase in a very different way. So, if I imagine I'm pointing this laser pointer onto the screen. If I could freeze time and then cut down into the beam, turn it around, I'll see all of these different waves. If I then select points on these waves that are identical, I can then connect all of these points or join the dots, and I'll be able to map out the entire phase of my surface. So I can think about phase working in that way. Now, to test the concept itself, we use a process or a field called digital holography, which is a little bit different from conventional holography. Because in conventional holography, you would need some sort of beam of light, like a laser beam, and you would need the object to actually exist. So in this case, you would split the beam up. The reference beam will then interfere with the object beam on a photographic plate. And if you want to view what the object looks like, you'll then shine the reference beam through this photographic plate. But in digital holography, we don't need the object to actually exist, because the object in our case would be a shape of light. And our photographic plate is what we would term the digital part of it. And we use a device called a spatial light modulator, where our digital holograms are addressed onto a little screen here that's made up of liquid crystals. And as we apply a voltage across the screen, then our molecules in the liquid crystals will start to bend. And as they start to bend, if I send light through them, then they'll be refracted a little bit. So I can imagine now that if I had to address my screen with a grayscale image of going from black to white in steps of maybe, 256, where each of these different colors represents a specific voltage, So if I've got a complicated grayscale structure on my screen, and if I shine a light beam onto it, then what comes out will be a modulated structure in phase. So again, how does this work? If I go back to my little waves here, and if I say that the first one starts with white, if I then had to add another level of gray, it will then shift one of the waves. And if I add another level of gray, which is slightly darker, and then eventually going all the way down to black, if I then had to join these dots, I find that I have a completely different phase structure. So that's basically how this device works. But how do we make these actual holograms? Well, we have our reference beam and we have our desired object. So effectively, we've got to go back to the old principle and simply just interfere them. And we can do this completely digital. And by interfering them, we can then basically send our desired beam or our reference beam onto our spatial light modulator. It's been addressed with this grayscale image. And then I can capture my little shark's logo or whatever other shape that you actually want onto a CCD camera. So that works quite well. Now, in terms of actually determining what the phase of the elements themselves should be, well, as I said, if we start with a Gaussian beam, now the reason this is called a Gaussian beam is because if I fit the cross-section of this profile, I actually find that it's a Gaussian function. That's why it's just called a Gaussian beam. But if I start with the Gaussian beam in some flat phase, so you can imagine all of those little waves are all perpendicular to each other and the phase would just be a complete straight line, so you wouldn't see any variation in color. But if I then had to design my first element with some complicated phase structure, the beam directly after this element would again be just a Gaussian beam, but it would have acquired all the phase from the element in itself. If I then allow it to propagate in free space to just before the second element, I'll be able to obtain a flat top beam of some complicated phase structure again. But I then take the inverse of that and I make the second element. And in doing so, I have an output flat top beam with a flat phase. So in theory, it seems to work quite well. But in practice, we obviously need to test this. And again, we use digital holography and we use a spatial light modulator. So we think about our first element and we design a certain phase structure. Now, how we like to test things specifically in the laser world is that we like to look at what we call a round trip. So I can imagine that although I'm going in one direction, I showed you from the Gaussian through to the flat top, that process needs to be repeatable throughout. So if I start at the Gaussian, hit the flat top element and come back, that's one round trip. And it needs to successively do that until it reaches its steady state. So in our case, we just need to sample a single round trip where we will start with the Gaussian beam, we'll pass it through our first element, which will be loaded onto the spatial light modulator. I can then measure what the flat top beam would look like just before the second element. But in order to do this, I don't want to use like thousands of SLMs. In effect, what I can do is, after I've achieved my flat top here, I've got to go through the second element twice. So I just combine it into one. This is what one element would look like, but if I combine the dual pass into a single element, I would get something that would look like this. And if I allow it to propagate again, I don't need to go through the first element again to identify the shape. Because as I showed you before, the shape just before and just after the element are identical. So it shouldn't have to be any problem. I can actually measure the beam as it's coming back just before the first element. And if I do so, I can then direct my flat top beam onto the second half of the spatial light modulator that's got this complicated phase structure, and then I can measure onto a CCD camera what the return beam looks like. So if I start with the Gaussian beam as such, onto the first element digitally, it gives me a very beautiful flat top. I then pass it through twice the second element, and if I look at it just before it reaches the first element, I see that the shapes are quite similar. More importantly, though, is that the sizes match very well, which is quite important. Because if the size was completely destroyed, then we would know that this process wouldn't work. This also looks a little bit dirty, but that's because we're limited to the device that we're using and the number of pixels that we have on our device. It's not a continuous surface. But as we can see, we started out with the Gaussian, we've come back with a pretty decent Gaussian, so we're quite happy. In this case here, we're just transforming the same Gaussian, but into a much larger flat top. So we have this kind of control, we have very much freedom with what we want to do. So we then take these digital holograms, we make actual physical elements out of glass from them, and then we can then test the performance of these elements. We then take our Gaussian beam again, we'll then propagate it through this phase element, And then we find that we have a very nice transformation of our flat top beam. And with the second element in place, and because this flat top beam has a flat phase, it propagates over a very long distance without changing very much, which is exactly what we want. But our design, what we have imposed, is that we wanted to do a more proof of concept type of test. So we didn't want to make our flat top beam too big, because we could encounter a lot of problems. So what we've chosen here is a flat top edge-to-edge diameter of 2 millimeters, and we had a crystal of 4 millimeters. So we're only expecting 50% energy extraction. But in terms of proof of principle, it seems to work quite well. So again, we go back to our little laser configuration here. We've got our 2 mirrors, our 2 optical elements, our crystal placed very close to the second element where the flat top beam would exist. And our point of comparison is against this configuration with no optical elements inside the cavity. So it's a direct comparison of brightness. And what we find, if there's no optical elements, we get these very messy shapes of laser light that comes out with very high power. And as they propagate into further space, you'll find that they change their shape and it rapidly evolves. But with the elements inside the cavity, we have these 2 very nice Gaussian beams coming out of the cavity. And as they propagate, they keep their shape very, very well. So just a quick one, if I had to use the same parameters in a very traditional laser cavity here, I would need a cavity length of 6.5 meters. Whereas with the design of these elements, it was only 0.5 meter. So I have so much more freedom to be able to work on this with. In terms of the brightness, we find that with the optical elements inserted inside the cavity at a much higher pulse rate, we have about a 3.5 times improvement in brightness. But if we had to normalize the energy, because as I said, we're only taking out 50% of the energy, if we normalize the energy and then redo all the tests, we get close to a 7 times improvement in brightness. So if I could propagate a beam by 2 kilometers, I can now propagate it to up to 5 kilometers, just by using this simple concept. So what's next? Well, we've been using these rod crystals, and we would like to actually go to slab crystals, because they have a much larger surface area for cooling, where again, we'd now want to transform a circular beam into a rectangular beam. It's going to be a little bit more tricky, but it'll be a lot more interesting. And with that, I'd like to say thank you.